All right, vectors in the coordinate plane. All right, so we are going to start introducing them in the coordinate plane, which is, I don't know if that's what you're familiar with or not, but it helps represent what you're familiar with in a right angle. And so if we have this vector here in the coordinate plane in a standard position, and even if it's not in a standard position, you can slide it to a standard position because it's going to be parallel and it's going to be equivalent. So you haven't changed anything if you put it in standard position. The angle measurement's the same from the horizontal, all right? So what actually happens is you can create this right triangle, right? The distance you have moved right or left is your x, and the distance you have moved up or down is your y, all right? And it matters because direction matters. It matters if you have a negative x or a negative y. It matters what quadrant you're in. If I'm in quadrant 1, I obviously have a positive movement left and a positive movement right and a positive movement up, right? And so it matters what coordinate you're in. We have what's called component form of vector, which is kind of hard to read up there. The component form of a vector AB with initial point A, which is your x1, y1, and terminal point B, which is x2, y2, is given by x2 minus x1 and y2 minus y1. So you're basically just seeing how you moved, right? How you moved. X1, Y1. So you're basically saying, well, I moved this many X's and I moved this many Y's. And that's what all component form is. Notice the notation for component form. It looks like kind of a broken parentheses, all right? Kind of a hard set parentheses here. That's your component form. So look at example 1. Find the component form of AB with the initial point -4, 2 and the terminal point 3, -5. Well, you simply take, remember, by the way, order matters. So it is the terminal point minus the starting point. So order does matter, okay? So we are going to say it would be 3 minus a -4 and -5 minus 2. So we would simplify that to 7, 7, -7. All right, so go ahead and try just A. All right. Magnitude, if a vector with initial point x1, y1 and terminal point x2, y2, then the magnitude or the length of the vector is given by this. And you notice the notation is the absolute value, okay, absolute value of the vector. It's the square root of the difference squared plus the difference squared. This should look vaguely familiar. What does that look like? Yeah, this is my distance formula because you're finding the distance, right? And so if you were to see this notation, if V has component form, so if you already have it in component form, then you can find the length of V by just doing the absolute value notation here, which tells you to do the distance formula. But you already have component form, so you already have your x2 minus your x1 and your y2 minus y1 in component form. That's what we just found. So if you see this notation, they want you to do the square root of the component form squared plus the component form squared. All right. So it looks like, hey, I don't have two numbers to do distance formula. They've actually already given you the x2 minus x1 and the y2 minus y1 if they give it to you in component form, because that's what we just figured out was component form. So find the magnitude of the vector. And they've given us the points -4, 2, and 3, -5. And so if we put that in component form, 3 minus a -4 is going to give us 7. -5 minus 2 is going to give us -7. And so we are going to get square root of 7 squared plus -7 squared, squared of 98. And I think they went ahead and rounded that to 9.9. This is pretty straightforward. If you have two vectors, k is a scalar, then the following are true. You can add the two vectors, you can subtract the two vectors, and you can multiply a vector by a scalar. We're not going to spend a lot of time here because this is almost like matrices. It's almost the same concept, right, as a matrix. We have w and y. They're bold, lowercase. That means we have two vectors. If you add them, you would literally just add -4 and 2. So if I'm doing this one right here, I'm going to add the first value or the x value there, -4 and 2, and 1 and 5, right? If I'm going to do something like b, you're going to do basically order of operations. So you have your z minus your 2 times your y. Order of operations says I need to apply the parentheses first, right? So I have -3, 0, minus 4, 10. -3 minus 4 gives me -7. 0 minus 10 gives me -10. So same concept as, any other solving that you've done over the years. So for the first one, you should have gotten -19 and 4. And the last one, 3 and 22. A vector that has a magnitude of 1 unit is called a unit vector. Sometimes useful to describe a non-zero vector v as a scalar multiple of a unit vector u with the same direction as v. To find u, divide v by its magnitude v. Think of this as units. Like if you are traveling 300 miles in, 5 hours, what is your unit? Well, that's 60 miles an hour, okay? So you've used units all the time. You use units all the time. Price per gallon, that's unit measure. Price per pound, unit measure. Miles per hour, unit measure, okay? And that's all they're saying here. That if you take the vector and put it in unit form, then that's what you're talking about, okay? And so that's all that I want you to know from that. What I do want you to understand is at the bottom of the page, it says unit vectors in the direction of a positive x-axis and positive y-axis are denoted with an I. I and j, respectively. Vectors I and j are called standard unit vectors, okay? And so standard unit vectors, you're going to use this when we get to word problems. So this is why I'm introducing it, because you can basically take a vector and slide it anywhere around on your coordinate plane, and it's not going to change what's happening when you talk about the trigonometry of a right angle produced by it, okay? Because if I were to have a right angle up here, that's great, but there's more information I actually need to know to solve it. So if I were to slide it down here and put it in unit form where it's butted right up next to my axis, it's the same vector. It has the same length. It has the same direction. I haven't changed anything. I've just literally translated it across the coordinate plane. And so because you're familiar with coordinate plane and right angle trigonometry in that setting, sometimes these word problems are easier to use it in unit form. And so I just want to introduce you to this concept so that when we start doing the word problems and sliding these guys around, you understand it's okay. We haven't changed the direction, the angle that it is, and we haven't changed the length of it. We have literally just translated it into like a unit. And I also want you to recognize the AI plus BJ. This is standard form. You have I and j as your standard unit vectors, and in component form, this is what it looks like. This is what it looks like. All right, so let's look at example 5. So we have DE is a vector with initial point -2, 3, and a terminal point 4, 5. Right, DE is a linear combination of the vectors I and j. What they want us to do is they want to just put it in component form, and then they want us to write it, the component form, the x value I plus the component form y value j. So the first thing we do is put it in component form. Remember, it is your end point minus your initial point, so terminal minus initial. So 4 minus a -2 is going to give us 6. 5 minus 3 is going to give us 2. That is our component form. And then we are going to rewrite it, just saying 6i plus 2j. That's what it looks like as a combination of vectors, So go ahead and do A really quickly. Just A. So you should have gotten then, for this first one, 8i plus 5j. Good. All right. Let's look at component form using information that they give us. Okay, so they give us at the top of this page, or in the middle of this page, they give us the magnitude times cosine is your cosine, and your magnitude times sine is your sine, okay? Which is the absolute truth here. That's how you solve this. And so they've given us up there. So they've given us component form here, and they're telling us that if I substitute this, I can get more information from what I have. Now, and you can go back and forth between the two. So why is this? So if we look at this particular problem that they've given us, they have given it to us on the coordinate plane. So we're going to see why they drew it like this on the coordinate plane and then how it helps us. All right. So they gave us this, and at this point in our lives, we actually don't know that. All right. So what we do know is it says magnitude of 10 and a direction angle of 120. Direction angle is telling me this is standard form angle. So I'm going to use it just like I would on the coordinate plane if I were doing a unit circle. 120 degrees in standard form starts at X and goes 120 degrees this way. When they tell me that it has a magnitude of 10, they have told me the length of my hypotenuse, 10. All right? And so from this, I can draw a right triangle. I can draw a right triangle from the terminal point down, right? And from the initial point over, right here. I can draw this right triangle. This is a right triangle. And then if that's 120, what is my leftover part right here? What is this? What is my angle that is going to help me, my reference angle here? 60. 60 is my reference angle. So if I wanted to find the component form, by component form I mean how far I move left or right and how far I move up and down, component form, then all I need to do is find my y value and my x value, correct? And so I can use trig to do this. And so that's why my y value is going to be the sine of 60 over 10. Why? Because the sine of 60 should equal y over 10. If I multiply both sides, I get 10 times the sine of 60. That is going to be my y value of my component form. Everybody see that? SOHCAHTOA, opposite over hypotenuse. Which means that my x value is going to be adjacent over hypotenuse, right? So it's going to be 10 times the cosine of 60. Now, I will tell you, because direction matters, depending on how you set up your triangle, the reason I teach it this way and not just memorize that it's XY is because there are going to be times you could draw your triangle and it's not that way. Because you could actually have drawn a right triangle up here, all right? And then all of a sudden your opposite would have been your X movement and your adjacent would have been your Y movement. So it definitely matters how you sketch your triangle as to whether it's sine or cosine, all right? Does that make sense? So when I solve this, 10 times the sine of 60 gives me approximately 8.7. And then 10 times the cosine of 60 gives me 5. However, direction matters. What quadrant am I in here? Which direction have I moved? Left or right with my... I've moved left. So what should that negative be? Should be negative, right? That 5 should be negative. I said, what should that negative be? Yeah, the 5 should be negative there because I moved left. It's very obvious that from my starting point to my ending point, I move left and up. So that tells me my final answer should be negative and positive, left and up. Okay? Left and up. All right, you should have gotten 5.7 for both. 5.7 for both. 8 times the sine of 45 and 8 times the cosine of 45 would have given you the same answer for both. All right, next page, direction of vectors. Direction. So when I am talking about direction, I'm trying to find the angle. I was just finding my XY values just now. Now I want to find my angle. So I'm not going to use sine, cosine, or tangent. What am I going to use if I'm backing into it and finding my angle?
The opposite.
So what uses opposite over adjacent? I mean, sine, yes, opposite over adjacent or sine over cosine. What is that? Tangent. And I'm finding my angle, so I'm going to use my inverse tangent. All right? If they have given it to me in this form, which is my x value?
3.
Positive 3. Which is my y value?
7.
Positive 7. All right? So, inverse tangent then of which value over which?
3 over 7.
There's a 50-50 chance, 7 over 3, okay?
That's right.
66.8 degrees. All right, let's look at this next one. They give it to me in component form. All right, component form. This one's a little bit trickier. What quadrant am I going to be in if I'm at 4, -5?
3.
Fourth quadrant, okay? So I'm going to still do my inverse tangent here. What happens when you plug in -5 force into your inverse tangent in your calculators? What happens? What? So you get -51.3 degrees. All right. Here's the deal. That is an accurate answer. However, I'm not going to give direction in negative degrees. All right. So how do I tell someone to get to -51.3 degrees if I actually want them to go all the way around the circle?
Subtract from
So 360, right? Minus your 51.3. Right. 308, I think is what it is, right? Running forward at 5 meters per second, throws a football with a velocity of 25 meters per second at an angle of 40 degrees with the horizontal. What is the resultant speed and direction of the pass? All right. Hopefully we have time to do that. Form, and I need the movement of the guy running in component form. They're both affecting it. And so I need to know the basis of this one, right? And I need to know the basis of the other one. So I am going to do my x value is going to be 25 times the cosine of, 40, right? And then my y value is going to be 25 sine of 40, right? Because we're 40 degrees, we're in the first quadrant, we're good to go. We'll do this on a coordinate plane tomorrow. That's my first one. And so I'm going to get something like this. My second one is simply just going to be 5 to the right and none to the left, none up or down, right? If I'm just moving a horizontal, I'm literally just moving right 5. If I were moving left, I would go left 5, -5, okay? And so when I combine these two, I add them together because that's the whole movement on that ball, right? The running and the throwing. So I end up with 24.2 and 16.1 if I add those two together. And now I can take my tangent to see the direction of that ball, my inverse tangent. And I would get 33.6 degrees, by the way, if I took that inverse tangent right there. So when you have